Hey, Organic Chemistry, how are you today? I'm excited. Let's continue our acid-base mechanisms discussion. So this is the third video. So if you haven't watched the others, you may want to pause and go back and watch the other two. This video, I want to focus on just flat out getting good at our mechanisms. I want to go all the way through the process with an acid and a base using our pKa table. We're going to try and figure out what everything is. We're going to add some terms, add our vocab to that, and then we're going to predict our products and write our products. We're going to list everything we can about this reaction and then turn around and do it a couple times. So we just get really good at acids and bases. Remember our number 4 definition. It depends what you mix with. So my goal is to actually give you stuff maybe you've never seen before and have you come up with a mechanism that is going to follow rules and work. So let's take these two compounds for fun. This is actually acetone and ammonia, and we're going to see what we can do with that. Let's treat it as an acid-base process. Let's figure out what would be the acid, what would be the base, and let's draw the products. And then I'm actually going to add vocab from Gen Chem 2 to that. And then we're going to predict whether or not this reaction would be a halfway decent reaction. In other words, would this reaction even happen or would it kind of suck? So how do we do that? Well, we learned in our last video, the first place we're going to start when we see something mysterious, we're going to start by drawing our structures, which I've done for us. Add in your lone pair and grab a pKa table. Let's see if we can't find both of these on a pKa table. Now, I posted one on your Blackboard. There's a million of them out there, and I've also put one at the end of this document. So I'm going to switch to my highlighter, and let's see if we can't find both of those on our pKa table. So you can see I put a bunch of examples in here. I'm super excited. So let's go to our pKa table, and let's see if we can find acetone and ammonia. I see ammonia, but it's over in this column. So not yet. Okay, you've got to be pretty careful. We are looking not as the conjugate, but this would be on the product side. We're looking in this column. This is on our reactant side. And you've got to match your charges. This is an ammonium. That's already got a positive on it. That is not what we have. Okay, so keep going. For some reason, I couldn't move there. All right, let's keep going. I do not see any of those yet. Aha, I just spotted acetone right here. And what is our pKa? 19. Okay, let's remember that. And then look at this right next to it. Oh, we're going to add this vocab. That's beautiful. Okay, so this is what's on our reactant side. This will end up on the product side. That's our conjugate. We're going to label those conjugates. And then what else were we looking for? Ammonia. Here it is, right here. Our pKa is 36. I love it. Okay, that is also on our reactant side. All right, so 19 and 36. Let's scroll back up to that initial example. We've got a pKa of 19 and a pKa of 36. Okay, so this one, our lowest pKa is our acid. I love it. And why do we do this first? Because as soon as we know our base and our acid, we know the direction of our mechanism. Let your mechanism not only explain what's happening in the reaction, but it'll also draw your products for you. You can predict this reaction. You can draw the products that are going to happen from your mechanism. It literally gives us everything. So if we know we have a base, remember our rule from the last video, we always draw our mechanism from where we have electrons to where we don't. So we are going to go from our base to our acid in our mechanism, and we have to have available electrons. So let's find the available electrons. For ammonia, we've already used ammonia. That's our lone pair. And then to an acid, we're going to draw towards either that available space or an available proton, hydrogen. We're looking for something there. Now, if this is something you've never seen before, your pKa table also gives you a little bit of a hint. I'm going to draw in my hydrogens just so we see what our options are, and it turns out our hydrogens are all right there. That's it, and they're all the same. So, in fact, if we're using this as an acid, that's our only option. So let's draw our mechanism and see what our product would be. So I'm going to take this lone pair on nitrogen, and bases take that hydrogen, and they leave behind those electrons. I love it. So now how do you draw that? Well, what did we just do to this acetone? We didn't do anything to this side of our molecule, but we did leave behind 2 electrons on that carbon. So if your carbon now has an extra electron, that's a negative. And then what did we do to that ammonia? Well, we just formed a bond here to that hydrogen. And now we've bonded that lone pair to nitrogen a little bit more than normal, so that's got a positive. Okay, this is awesome. So this is our salt. We just made our salt. And our mechanism drew that process. We literally left behind this lone pair and we formed that bond. That's why I love to color code. We're going to track everything. Okay, now let's add some vocab. So in an acid-base reaction, your acid, the acetone, look what it turned into. This is a little bit of Gen Chem 2 review. Your acid has now turned into your conjugate base. And now your charges should match that. They should either be neutral or negative. And in this case it is. Look, our carbon is negative. And then your base, look at our base, turned into a conjugate acid. And look, do your charges match that? Acids are either neutral or positive. And yep, sure enough, our nitrogen is positive. So we're going to keep in mind this pattern. Our pattern will always follow this. Your acid turns into a conjugate base, and your base will turn into a conjugate acid. Oop, let's color code that pink. I'm feeling that that needs to be pink. Okay. So now let's scroll for a second. I want you to keep this structure in mind. That is our conjugate base. And let's scroll back to our pKa table. OMG. Your answer is already on your pKa table. Look at this. Let me erase my little highlighter so we can look at it again. Look at this structure. This is our acetone. Look at this column. This is your conjugate base. So this column is telling you which conjugate base to form. It also is telling you, which hydrogen was taken in that reaction. Look at the negative right there on that carbon. So that is literally telling you that is your product in that reaction. That's why I love this pKa table, even though it looks a little bit old and well used. It's because you have both your acid and your conjugate base listed. And why does it have only acids? Because it's our pKa table. If it were a pKb table, it would be opposite. All right, so this is awesome. Let's go back up to our vocab, and we're going to add one more piece of information. That piece of information is an additional pKa. We have a pKa for our acid. Let's get a pKa for our conjugate acid. And then we're going to compare our equilibrium. So if our acid is 19, let's find our conjugate acid. Why the acid? Because that's the A in pKa. We're looking at acids. Now we can hit up that NH4 number on our pKa table. There it is. Here is our NH4 plus, and that is a pKa of 9.3. Now you see how these are opposite? That's because ammonia was our base. Okay, our pKa is 9.3. Let's add that in there. Ooh, I hope you're not getting dizzy watching this video. Okay, 9.3. Why do we care? Because Mother Nature will always have equilibria lie towards the more stable. Will be towards the more stable. Okay, so let's work our way through this. The lower the pKa, the more acidic. We've got that one down pat. The more acidic, the more reactive. The more reactive, the less stable. So we're in fact going to compare these two pKa's, and we're going to go toward the higher one because we want to go toward the more stable. So if we're picturing this equilibrium, we're in fact going to favor backwards, not forward. And that's telling you that that reaction kind of sucks because you're looking at a pKa difference of 9 and 19. Remember, that's not a factor of 10. This is a log scale. This is much larger than that. That is a factor of tenfold. All right, that is 10 to the 10 different. That is a lot different. That means that reaction is very much favored in this direction. Okay, that's going to be important. So let's turn right around and get really good at this. Let's do it again. Let's pick another example. Let's label acid, base. Let's predict our products, and let's label conjugate base and conjugate acid. Let's just turn right around and do it again. And we're going to do it for another set of things that you've maybe seen or maybe not seen. I'm pretty sure you've seen these, but let's get really good at just labeling all of this stuff. All right, so where do we start? Put in your lone pair. We need to know where we have electrons. If you were to just look at this on inspection, you have electrons on both compounds. How do you know which one is which? You don't. So let's look at a pKa table again. And let's look for our pKa of acetic acid and our pKa of water. And let's see what we've got. So seriously, I just thought I was being really good at including the pKa table. I didn't realize it would feel like a roller coaster when I was scrolling back and forth to look for our pKas. So let's just erase here and let's see if we can find our acetic acid and our water. Okay, I don't actually see them on this one. Do I? Yep, never mind. All right, here's water. pKa 15.7. So let's write that out. And then let's scroll up and see if we can't find that acetic acid. Oh, there it is. pKa 4.7. Okay, done. Let's go look for that then. Let's write those out. We've got a pKa of 15.7 and a pKa of 4.5. Okay, which one's the winner? We've got acid right here and base right there. Okay, so water's a base. Water could be an acid or a base. And what's our rule? Just depends what it's mixed with. We have either one. So what do we do next? We look for our available electrons. That's our lone pair. And now we're looking for an available hydrogen in our acetic acid. Well, we actually have two different hydrogens. We have one here, and we have 3 hydrogens out here. If you're not sure which one to take, the chemistry answer is the one connected to the electronegative oxygen, also the one that has a resonance pair. The cheating answer is to go look at the conjugates on your pKa table, like I just taught us. Okay, so we're going to take this one. So how do we draw this mechanism then? We are going to go from base to acid. So we're going, and this is where I like to draw out structures. Okay, this acetic acid has a bond there. So we are going to go from base to acid. And now let your mechanism help you draw your products. And now we've got a negative on that oxygen. You're not sharing as much as normal. And what happened to your water? Aha, that lone pair is now a bond to hydrogen. And now we have H3O plus. Okay, here's our salt. I love it. All right, now let's label each one conjugate. Remember, your acid turns into the conjugate base, and your base turns into the conjugate acid. Okay, there we go. Done. So then what's the next pKa that we need? We need that pKa of that conjugate acid for H3O plus. Let's scroll down and see if we've got that. And I am pretty sure we do. Look at that. There it is, right there. Oh, and here's the cheating conjugate version. Okay, what is our hydronium ion? Ooh, negative 1.7. Son of a motherless goat. I bet that's going to win, right? If you were to compare acids, that's the stronger acid, negative 1.7. So then which way is our equilibrium going to lie? Is it going to lie towards this direction? Heck yeah. We're comparing 4.5 and negative 1.7. So our equilibrium would actually lie towards reactants. Okay, I love it. So now I'm going to leave you with one that you should try. What? It's backwards. So I'm going to stop here, and then the next video I will start with this one. So once you get really good at going forwards, we love organic chemistry because then we turn around and go backwards. So I'm going to leave this as a cliffhanger, and then I'll start my next